So for the third talk of the morning, it is a pleasure to welcome Phillip Wesolek, who is going to talk about approximating simple locally compact groups by their dense subgroups.
Thanks, and thanks to the organizers for the invitation. So I'll speak about some joint work with Pierre-Emmanuel and Colin Reid. And I think we've sort of cyclically permuted the order today. Uri started with deformation, Katie talked about quasification, and I will end by talking about approximation. So my talk will be a bit of the same format as Katie's talk. I will give sort of a general overview of simple locally compact groups, in particular beyond the Lie setting, and then move into the work that we did. I think the one thing I'm hoping is that I convince you that there are many very interesting simple locally compact groups out there, and hopefully get you thinking about them. Okay, so let's just start with a few very basic definitions. So a locally compact group, which I'll denote LC, is totally disconnected, which I'll denote TD, if the only connected subsets are singletons. And the sort of groups that we'll be interested in studying are those that are topologically simple, which means that the only closed normal subgroups are the trivial group and the group itself. Now, I'll often drop the topologically, and there's a couple reasons for this. One is it's sort of annoying to say. The other is that we don't actually know of a compactly generated locally compact group that's topologically simple, but not simple. So this is if I had to guess, I would say that yes, these things exist, but we don't know what they look like. And in fact, there's many restrictions now on what they could possibly look like due to work of Pierre-Emmanuel and Colin and George Willis. Right, so I think the best way to think about these things is to start with a bunch of examples. So what are examples of simple locally compact groups? So as we've seen a lot of the simple Lie groups, and I think one thing that's not said enough is where the topologies come from. So SLNR becomes a locally compact group by seeing it as a closed subgroup of R to the n squared. The simple algebraic groups over non-Archimedean local fields. So I put that in quotes because there's many adjectives that have to go along with this to make this a sensible thing. But we're now over non-Archimedean local fields, and this is something like PSLN QP, and this thing inherits its topology in the same way, where QP is the collection of p-adic numbers. Now, the example that I think are the most instructive when thinking about simple, or that have the properties that generalize most easily and give you insight into what sort of the groups look like generally, are the groups acting on regular trees. And so for this example, I'll actually spend a little bit of time because I'll refer back to this several times. So many groups acting on regular trees. So Katie alluded to this, but let's just do it carefully. So let's think about the automorphism group of the three regular tree. So what's the three regular tree? You take a graph with countably many vertices such that every vertex has three neighbors and there are no cycles and it's connected. So it looks like that. Now, there are sort of two types of maps that you can have here. You could have rotations and you can have, say, translations. And it's easy to convince yourself that you can produce continuum many automorphisms of this thing. So it's a very big group, and when you have a really big group, what you do to deal with that is you give it some topology. So I also think that one thing to say carefully is that what is the pointwise convergence topology? So we topologize at T3 with the so-called pointwise convergence topology. And what is that? It's for all finite, let me say, a sequence of automorphisms converges to an automorphism F if for all finite collection of vertices, let's call it F contained in the vertex set of T, there exists some n such that for all I greater than or equal to n, and for all v in f of I of v is equal to f of v. So yeah, I think it's a very nice and natural definition that reflects the combinatorial nature of this metric space. And what's this little plus? Well, this is an index 2 subgroup of this thing. It's a group generated by edge fixators. You take all the edge fixators and generate them. This thing is simple by work of Tits. Another very cool group is these so-called Berger-Moses groups, where this one will act on the 7 regular tree, and you fix how it looks like locally. So here, the local permutations have to come from the alternating group. So these are the kind of groups that I encourage you to keep in mind for the talk, because these are really sort of indicative, I think, of what the generic simple locally compact group looks like, in my opinion. People disagree, but. Now, another class of groups that I like a lot are the tree almost automorphism groups. So let me just tell you what these are, because these are a lot of fun. And so what is a tree almost automorphism group? So we know that you can take a boundary of this thing. And the boundary of this thing is a Cantor set. And the automorphism group of T3 acts on this by homeomorphism. So you can take the topological full group, and how do you define that? You say it's a collection of homeos of the boundaries, so that you can cut this into finitely many clopins, and on each piece of the clopin it acts like one of these automorphisms. But it doesn't have to be the same one, obviously. And so this gives you a rather exotic locally compact group. How you topologize it, you have to be a little bit careful. But this group was the first example of a simple locally compact group without lattices, which is due to Bader, Caprace, Gellender, and Moses. And so these groups I like a lot, and I think they're surprisingly tractable to study, depending on how you ask your question, because they inherit a lot of regularity properties coming from the tree automorphism group, but at the same time, Thompson's group F lurks in here. So, okay, so what are some other examples? So certain Cass-Moody groups, if you're curious about those, you should ask Pierre-Emmanuel. Certain groups acting on cat 0 cube complexes. So the set of examples that I think are very cool is Lazarovich has these very homogeneous cat 0 cube complexes that admit locally compact automorphism groups that are simple. Much of the machinery for trees goes through in that setting. One that I should add here is, I should put 7, is buildings. In particular, Uri mentioned hyperbolic buildings, and Ann Thomas has done a lot of work, and Tom Demetz have things looking at the automorphism groups of certain buildings, and that also gives you examples of simple locally compact groups. So the remark is that of this list, the only connected ones are 1. All the rest of them are totally disconnected. And so so maybe in 2 you have some kind of connectivity because you have a Zariski topology around, but once you get outside of that, all of these things you need sort of different techniques to study. You can't sort of rely on algebraic techniques anymore. So you see the big list and you say, okay, well, simple Lie groups, those things have a nice classification. We can get our hands on those. Simple algebraic groups, I believe that, again, we have algebraic techniques. For the rest of these, it seems rather wild. You have groups coming from geometry, okay, groups coming from dynamics, groups coming from, I guess, buildings or weird Lie algebra type of things, groups coming from geometry again. It's not clear that you should expect too many general theorems. But what's sort of become apparent in the last, maybe 15 years is that indeed there is common features between all of these groups. As soon as you become totally disconnected and simple, you can start saying general things. And I think the sort of guiding principle that I like is the following quote due to Cartan. Sorry, that's the next slide. I jumped the gun. Okay, so before I get there, I should say, so what do all these groups have in common just on the surface of them, 2 through 6? So the class of groups that we'll study is the class S, which is the class of topologically simple, totally disconnected locally compact groups that are non-discrete and compactly generated. So let me write this definition down because I'll appeal to this all the time. And the point is that all of these groups that are disconnected lie in this class. So the class that we're interested in is this class S, which is the class of compactly generated t.d.l.c. that are non-discrete and topologically simple. And if you prefer to think about examples, you have things like aught, t.d. plus, you have things like these Berger-Moses groups, and you have things like almost automorphism groups, and you have things like p.d.l.c. groups or algebraic groups. So this is sort of the family that we're interested in. This is the family we're interested in studying, and we see it contains a lot of groups that we like. And in fact, it contains a lot of groups that we like. So a rather spectacular theorem due to Simon Smith is that there, in fact, continue many non-isomorphic groups in S. So it's a huge class, especially if you're thinking about simple locally compact groups. In the least setting, there's only countably many. And even if you throw in the algebraic ones, there's only countably many. Here, you see that there's, in fact, many. And these groups are there's many groups in S, these disconnected guys. And the fact is, this is not this is very constructive. He writes down very explicitly what these things look like.
Talking about simple groups?
Yeah. So he gives continue many non-isomorphic groups, which are topologically simple, non-discrete, and compactly generated. Right, yeah, so the thing here is the non-discrete, right? Yeah, so, and the thing is that this isn't some crazy construction. This is, in fact, a generalization of the Berger-Moses construction. And so you can really get your hands on these. And so I think this is a very exciting and interesting class to study, and what you can say about them, and sort of maybe a naive question is, what do the lattices look like in these things? Because we know what lattices look like in aught t for t a tree. These things are some kind of, they act on a biregular tree, but I think this is a very nice class, and also shows sort of the breadth of this class S. So you see this and you say, well, okay, you have this huge class. It's not clear that it admits any general theorems, especially when you're thinking about this sort of variety of examples that you can get. And in what I was saying a bit earlier, out of order, is that in the last sort of 10 years, we're starting to see that there is, in fact, general results you can say about this class. And the guiding principle that I like is the following quote due to Cartan. So it's kind of a historical law that the general properties of the simple groups have been verified first in the various groups, and afterward one has sought and found general explanations that do not require the examination of special cases. And hopefully by the end of my talk you'll see that, in fact, yes, well, I'm hoping the theorems I give you convince you that this kind of program of trying to find general explanations is a good one, and it's a tractable program. Right, so that's a bit the introduction, and now we go on to what we did. Maybe ask, is there any questions on these examples, or how to keep these in? So I think the good example to keep in mind for all of the theorems that we talk about is maybe you don't want to do 3, maybe you want to do 5. And you'll see why in a second. But this is sort of the example to keep in mind when you're thinking about these theorems and what they look like. So what did we do? So this sort of starts as a bit of a story, which involved Colin coming to Belgium 3 times and us having various conversations that led to this. So where does the story start? So the story that led us into this project has to do with an older theorem of Colin's. So let's remember that a profinite group is an inverse limit of finite groups. And so what's sort of your favorite example? If you take just the free group and take the profinite completion. So we've seen this several times this week. And now a theorem of Van Denzig says that these totally disconnected locally compact groups admit a basis at one of compact open subgroups, and these are all profinite groups. And back to our example, what do the profinite groups look like here? Well, they're vertex stabilizers in our tree. And if you look at this topology, and you take a stabilizer of a vertex, you get a map, you'll get a representation into an infinite product of symmetric groups that correspond to the permutations on the balls. And so it's sort of a fun thing to write down if you're bored and want a fun exercise, verify that the point stabilizers are compact in aught-t. So profinite groups enjoy a CELO theory which comes from the inverse limit construction. So if you've never seen this, you take what you know from finite group theory and you add pro after everything. And that gives you the CELO theory for profinite groups. Now, what Colin showed is the following, is that if you have a t.d.l.c group and you take a compact open subgroup and you look at a pro-p CELO subgroup of U. So where U is some compact open subgroup, which we know by Van Danzig's theorem is profinite. So we'll just write the setup over here. Oh, I shouldn't erase the, well. So the setup is we have G t.d.l.c, and we have U some compact open subgroup, and we have U of p contained in U a pro-p CELO. Now, in general, this thing is very small. Right? This thing is extremely deep inside this group. This will be, say, a continuum index. Like the pro-p subgroups they're very small, and it's really not clear that the group G knows anything about these, or should, right? If you sort of bury this CELO subgroup so deep inside the compact open subgroup, why should your group know anything about it? But what Colin proved is that there's a canonical t.d.l.c group denoted G sub p, which admits U of p as a compact open subgroup, and there's a continuous injective homomorphism from this group G of p into G with a dense image. So, so what do we have here? We have this G of p, which maps into G, and in here, U of p is really big. U of p is some compact open subgroup. So this group somehow knows about U of p. And for the experts, what this is, as a group, it's the relative commensurator inside of G of U of p. So you get this very large group that somehow knows something about the CELO subgroup, right? Because the CELO subgroup is open in there. So what several things Colin proved in his article is he proves that this, well, he calls it the p localization. He also proves that it's independent of your choice of compact open subgroup and your choice of CELO p subgroup. So, and independent up to topological group isomorphism. So this thing is really a canonical object associated to G. And again, this is also rather surprising because you have many compact open subgroups and many CELO p subgroups. So it doesn't matter how you choose these. You always get the same localization. And as soon as U of p has infinite index, this CELO subgroup has infinite index in U, then this map is not onto. So it really is an approximation. And if it's infinite, then this localization is non-discrete. So as soon as you have some kind of real CELO subgroup around that's not a finite index subgroup and is not finite, then you get a non-discrete group that maps into your group with a dense proper image. And so what our starting point was, well, this seems to be a cool thing. It seems to give us a way to approximate a group we might be interested in by...
UP is the p CELO.
Correct.
Now what is U?
U is a compact open subgroup. So this guy is a compact open subgroup in U, and this thing is a p CELO subgroup of...
Like if you take the example of like just a standard p-adic analytic group, like
Those are locally pro-p though.
What?
Those are locally pro-p. So it's right. They have a compact open p subgroup. So in that case, this is a finite index subgroup of that, and this map is onto.
Oh, US.
Yeah. So it's better to keep in mind something like, think about aught t5 and look at a 2 localization. Yeah, and actually we'll come back to that. But good question.
Could you even just give an example, just in the case of an ordinary profinite group? What if I start with the p CELO subgroup of that?
Sorry. Yeah, so in that case, what you get is the commensurator. So what I say is that it's actually the commensurator in there. So if you think about something like an iterated Reith product, so let's do this branch group, which is an infinite iterated Reith product of sim5s. Now, let's take a 2. So what's the CeLO 2 subgroup of this? Well, it's a 2 group of this thing. Let's just call it F. So this is the CeLO 2 subgroup of this guy. So that's the CeLO 2 subgroup. And what does the commensurator look like? Well, it's so this is self-normalizing in here, so you don't have to worry about that. So what it looks like is, let me write it up here. Yeah, maybe I write it a slightly bigger. So we take W equal to this inverse limit of iterated Reith products of sim5s. W2 is equal to the inverse limit of, sorry, I should put F there, so that's easy. Where F is CeLO 2 of sim5. And then what is this com? Well, the commensurator in W of W2 is where you allow finitely many sim5s, and then you have Fs off to. And it takes a little playing around to see that. But so in this case, we actually know very well what this group looks like. You're welcome. Good question. Yes?
Did you assume that G is in S? On this?
No. This actually works everywhere. Right? It's rather surprising. Yeah, it doesn't.
Why is it surprising? It's pretty trivial statement that it's independent choice.
No. The fact that it's
of the four finite are all conjugate, and up to commensurability, the commensurator is not important. So.
Yeah, I mean, you still have to do something to show the commensurator is dense, though, right?
But maybe the commensurator is everything. If you take product of, I don't know, SL2QP and SL2Q3 and SL2Q5.
No, but if you take an element, you take.
Yeah, I mean, so the commensurator is dense. So I guess it takes some work to show that, and it's sort of thinking about profinite groups. It wasn't immediately clear to me that you would always get a dense commensurator. Yeah, it uses a Frattini type thing, and I mean, yeah, it's not super difficult, but it's not something that I would have sort of guessed at right away. And that's actually a good question because it leads to another question that I'm curious about is, can you do this with other canonical subgroups? Like, I always wanted to know if a system normalizer has dense commensurator, or under which conditions a system normalizer has dense commensurator, per se. If you take a pro-soluble group, and it's the intersection of a CeLO system. So, a pro-soluble group can be written as a product of CeLO subgroups. It's a CeLO system. You take the normalizer of each piece. So it's called the system normalizer. That thing, again, has this nice Frattini type of behavior. It's unique up to conjugation. But it's not clear to me that has a dense commensurator. I think in general it doesn't. But yeah, maybe we can chat more, actually, because that's something I'm curious about. Anyway, so what's our starting point? So what we thought is that, well, okay, we have this localization that's locally pro-P. What can it tell us about groups in S? The other thing is just, what do these things look like? They're somehow really canonical. And in particular, what about something like, if I take T5 and I look at a 2 localization? That seems like something I should be able to get my hands on and understand what it looks like. So this is sort of, I think, at least my starting point for this, for trying to understand what, trying to understand these G of P things, and then what kind of properties do they have? In particular, what does that group look like? Right.
Sorry for interrupting.
Yeah.
I'm confused about the point. If you take a product of two groups like SL2Q3 and SL2Q5, I mean, I'm puzzled by this not onto statement that you have.
If it has infinite index. So in that case, you have the commensurate. Well, so if you wanted to look at like SL2ZQ or something, right? What's the commensurator of that? Well, it's commensurated in right? It's a commensurated subgroup. Because one half of the group centralizes it, and then it's commensurated in the other half of the group.
So this map G3 to G is...
Oh, sorry, yeah, I should say, you have to be careful. No, wait. What's going on there?
Proper subgroup.
It's not onto...
I mean that it's a proper subgroup. define it as a subgroup.
Oh, right.
I mean, for that you need
What?
also you need UP. I mean, if UP is finite, also.
Yeah, QP is fine. I mean, the point is if it's on. Oh, sorry. The point is if it's onto, this thing is locally pro P, so this has to have an open pro P subgroup, right? So, I mean, so if this map is onto, this thing has an open P pro P subgroup. So the image is then a closed pro P subgroup in here that has to be of. I see. The point is that this. Okay. Yeah, I see your point, because the thing is that this thing is not a second countable group. Yeah. So in the case that this is second countable, there you go. Yeah. So the answer to your question is, I should say if this has finite index and this thing is second countable. That's what I should say. Because then that rules out your case, because your ZP is, your SLN ZP is very deep in this group. But yeah, so there should be a second countability assumption here. That's what I should put. Sorry about that. Right. Okay. So what did we do? So, well, what one often does in mathematics is you sort of step back and say, well, if I have, let's just try to generalize what the properties are of these P localizations. So a dense locally compact subgroup of a locally compact group G is a locally compact group H such that it admits a continuous injective homomorphism with dense image. So this is sort of the key idea that we're trying to exploit. So but what we have in mind is, of course, these P localizations. Or what was the motivation? Now, a few remarks about this. So the first one is that when the P localizations are non-discrete, well, they arise naturally in the form of these P localizations, and they also appear, they should maybe give us tractable or useful approximations. And why is that? Well, they somehow keep track a bit of the topology. You don't totally lose the topology. On the other side of the coin, the discrete dense locally compact groups always exist, but it's not really clear how much information they give us. At least seems to be a much harder question. And so because we had this example of the P localizations in mind, we decided to focus on the non-discrete groups, although this is an equally interesting question and has been explored in various contexts. And I think I won't say, I'll just say that, yeah, this seems to be a much more difficult question, and these seem to be not as good of an approximation in general. So for example, all of your p-adic Lie groups admit dense-free subgroups. So our idea was to use the non-discrete dense locally compact subgroups to study groups in S.
Find the finitely generated dense subgroup also?
Yeah, in sort of like Q, PSL 3QP.
No, in those I know, but in the general case?
No. I think, so that's an open question. So take the almost automorphism group. It's not clear to us that has a dense-free subgroup. So yeah, that's a nice open question in this way. Yeah, do all these have dense-free subgroups, or maybe the examples that we like? Yeah, I don't know. I even think for the Berger-Moses groups, it's not known for like U of alt 7 that I had written down.
You say free subgroup, but I'm asking about finitely generated subgroup.
Yeah, I think it's in either case it's not. Yeah. So our idea was to use the dense locally compact subgroups to study groups in S. And that led us to the following class. So when we were thinking about this and trying to look at the examples and trying to compute things, the non-discrete dense locally compact subgroups, although in principle they should be good approximations, seem very different than the groups in S. So the first thing is that dense locally compact subgroups need not be compactly generated. And for specific examples, if you look at the 3 localization of this thing, that's not a compactly generated group. And the other thing is they don't even have to be simple, is that you lose simplicity. And the example here is that in plus of T5, it has a non-discrete dense locally compact subgroup that's not simple. And it's one of, if you've seen these groups by Adrien Leboudeck, it's one of those that lives inside, that's a dense subgroup of this, but it's not simple. So we're trying to get at this, and one of the big problems was that a lot of things that had been developed for locally compact groups always rely on compact generation. Compact generation is some kind of finiteness assumption that helps you out a lot. And so we had to get some perspective. And so what did we come up with? Sort of on a very meta level, we have P a property and G a group. We say that P is a local property if it holds of arbitrarily small compact open subgroups. So you could say your group is locally pro-P, which means if you go small enough, everything's a pro-P group. Neighborhoods of the identity all look like pro-P groups. On the other side of the coin, we had this idea of a regional property. So it's something that holds of arbitrarily large, compactly generated open subgroups. And so the picture is sort of, or maybe the slogan is better than the picture, is that local properties, you need your magnifying glass. Regional properties, you just need your eyes. And global properties, you need your telescope if you're thinking about a non-compactly generated group. So this regional property is somehow in between local and global. A few remarks about this. If you have a compactly generated group, then regional is equivalent with global, is that there is no difference between these because of this arbitrarily large thing. If it holds of arbitrarily large compactly generated open subgroups and your group is compactly generated, it has to hold of your group. On the other hand, for non-compactly generated groups, we start seeing a difference here, and this starts being an important distinction between regional and global. Regional properties often fail to be global properties, and the example is if you think about a regionally compact group, it doesn't have to be compact. So regionally compact would mean that arbitrarily large compactly generated open subgroups are compact. That's not the same as being compact. It's and a good example of a regionally compact group that's not compact, if you look at our favorite example, T3, and you look at a stabilizer of a boundary point, the set of elliptic isometries is regionally compact but non-compact. And in the literature, this regionally compact is sometimes called locally elliptic. But it starts showing you that these regional properties can really separate from global properties for non-compactly generated groups. And this has ended up being an important conceptual distinction for us when studying these dense locally compact subgroups because they need not be compactly generated, as we've seen. So what's the definition of the class? So a t.d.l.c group is regionally faithful if there's some compactly generated open subgroup O, such that O admits a compact open subgroup U, such that its normal core in O is trivial. Of course, we should just take some time to analyze this a bit. So you say some, not all arbitrarily large, but this property is inherited upwards. If it's true of some compactly generated open subgroup, then it's true of any supergroup of that thing. So this gives us, so what's the idea behind regionally faithful? Is that it turns out that this is some kind of weak form of compact generation. If you have something that you like that's true about compactly generated groups, it may well be true about regionally faithful groups. So it's some kind of weak form of compact generation. The other definition is that a group is monolithic if the intersection of all non-trivial closed normal subgroups is non-trivial. And we call the monolith the intersection of all non-trivial closed normal subgroups. So what's sort of a trivial example of a monolithic group that's not simple? So take the alternating group on 5 elements, take a countable power, and then act by shifting. The monolith of this group is this base group there. So again, sort of an easy exercise to see, but that's obviously not a simple group, but it is a monolithic group. So being monolithic is some kind of, it's some kind of control over normal subgroup structure. It's a far cry from being simple, as we see, but it's some kind of control over normal subgroups. So our class is the following. So a t.d.l.c group is robustly monolithic if it's one monolithic. So you intersect all non-trivial closed normal subgroups, you get something non-trivial. And the monolith is non-discrete, topologically simple, and regionally faithful. So what you should think about here is that this monolith somehow looks a lot like groups in our class S that we like, although you had to replace compactly generated with regionally faithful. And so this is somehow an approximation of the group in S. And you have to kind of allow for noise on top, which is this, the fact that you're only looking at the monolith. So we denote it by R. And sort of a trivial observation is all the groups in S are robustly monolithic. Well, they are their own monolith, and we just said regional faithful is a weak form of compact generation. So it's in particular compactly generated. So compact generation is enough to give you regional faithful for simple groups. So what's our theorem? So the sort of the big theorem that we're able to prove, or well, one of them, is that the class of robustly monolithic groups is closed under taking non-discrete dense locally compact subgroups. So it means if I have a group in this class and I find a dense locally compact subgroup, it also lives in there. And what this gives us is that R contains all non-discrete dense locally compact subgroups of groups in S. So in particular, when I take my P localizations of something from my class S, I land in this class R. And so this gives me a place where if I can prove some theorems about R, I can prove theorems about dense locally compact subgroups of S, in particular these G of P's. So let me just give you let me write R down here. So R is robustly monolithic t.d.l.c groups. And this is a proper extension of S. And that's because it contains these strange dense locally compact subgroups that we've seen. For example, it contains, aught D4 of 3. Lives in there, but that group is not even compactly generated, so it's certainly not in S. So what is sort of how did we prove this? I mean, at the end of the day, the proof is, it brings together a lot of pieces from the literature that tell us something about normal subgroups, but the kind of key observation that got everything going is this following rather trivial lemma. So if you have a group that's acting on a connected graph gamma, and you suppose that R is some subgroup that acts vertex transitively, then if a point stabilizer contains a non-trivial normal subgroup of R, then the kernel of the whole group acting on this thing is non-trivial. And so the proof is a triviality. So what's the proof? If you take something that's contained inside of this intersection, which is normal in R, this thing must act transitively because you can conjugate it around using R. And so it lives inside of the kernel. And so this was really the way to understand dense locally compact subgroups of groups in this class. Right. So probably one of the most important closure properties of this class is the following theorem. So suppose that G is a t.d.l.c group and we have some directed system of compactly generated open subgroups that exhaust the group. And so we're not assuming G is compactly generated or anything. Then G is in our class R that we like is equivalent with, there is some element of this directed set so that for every higher index subgroup it lives inside of R. So what's the point here? The point is that R, if you tell me the definition of R, and we think back to our conceptual perspective, that you have local, regional, and global, the definition of R seems very much a global definition. You have to ensure simplicity and these kind of things. What this is telling us is that R is in fact a regional property. And this is really the strength of this argument, this gives the class really a robust nature, is the fact that it's given by a regional condition as opposed to given by a global condition. Because global conditions tend to fall apart if you're looking at a dense embedding, where regional conditions tend to have a bit more staying power. Yeah, so this is, I think this is one of the results from our work that I was, on sort of a theory level, I thought was the most exciting. Right. Okay, so now we have this general class R, we've proved some things about it, we've amused ourselves, but the question is, the whole point was to say something about groups in S. So let's try to use what we know about, let's try to prove things about R to tell us things about S. So an old theorem due to George Willett, well, it's not an old theorem, it's a theorem due to George, is that the groups in S do not admit open solvable subgroups. And so this is a generalization of the sort of well-known result that if you look at a simple p-adic Lie group, you have no open solvable subgroups because you have a simple Lie algebra. So we generalize this to the setting of R, and of course if you know that this can be generalized, this also admits the same generalization, but I don't want to introduce too many definitions. So these things also do not admit open solvable subgroups, any of the groups in R. And this is a rather more complicated argument because here you use compact generation in an important way. Here you have to work a bit harder. But it's the regionally faithful is what gets you there. And yeah, so a more general statement holds, but I don't want to weigh you down with too many definitions. So now we know something about R. But if we know something about R, we know something about dense locally compact subgroups. So in particular, if we have a group in S, and we take a compact open subgroup, and we take an infinite p-CELO subgroup, then this thing's not virtually solvable. So we can say something about what all the p-CELO subgroups look like. Like you never have virtually solvable p-CELO subgroups living inside of a compact open subgroup in a group in S. And to put another way, it tells you something about the abstract commensurators of just, if you are interested in abstract commensurators of profinite groups, this is telling you something about what that huge space of abstract commensurators looks like if you, say, have a solvable pro-P subgroup. So the proof, I mean, is now a triviality. So we take the P localization that Colin built. It's a dense locally compact subgroup of G. So it's an element of R, because R is closed under taking dense locally compact subgroups. So we take something in S, we take a dense locally compact subgroup, it lies in our class R. So we deduce that it does not admit open solvable subgroup, so it's not virtually soluble. So we get a theorem which sort of fits with this, this idea of Cartan that you can prove general things about simple groups. And the way that we do it is we go through this class R because it allows us to analyze all of these approximations. So another application of this form is for a set of primes pi, a profinite group is a pro-pi group if every finite quotient is a pi group, which means that the order only involves primes from pi. The other way to think about it is it's the inverse limit of pi groups. So it only involves the primes coming from pi. So Pierre-Emmanuel, Colin, and George in 2013 proved this theorem for the class S. They proved that if you have a group in S, one of our simple groups that we like, and there's always a finite set of primes such that G is locally pro-pi. So it admits a basis, admits arbitrarily small groups that are pro-pi. So we realized that we could prove this, in fact, for R. So there's a finite set of primes pi such that G is locally pro-pi if you take a group in R. Now, with this, and with the added flexibility of R, because remember we said, okay, so R we have this monolith that looks a bit like a compact, looks a bit like something in here, but you have to replace compactly generated with regionally faithful, okay? But we also have this flexibility of what goes on top of that simple monolith. And that flexibility seems to be extremely useful. And in fact, we get this corollary. So if you have a group in S, then there's a finite set of primes pi such that for any locally compact group that acts continuously and faithfully on G by automorphisms is locally a pro-pi group. So it's a t.d.l.c group and it's locally pro-pi. So we can say something about the full automorphism group of groups in S. And this is rather striking to me because you think if you study locally compact groups outside of the connected setting, the automorphism groups can be huge. And what this is saying is that we actually have some control over the automorphism groups. So the automorphism groups of a locally compact group are one of these Polish groups that Katie was talking about.
Group in S. Look at all possible dense groups in it. and look at all the pies that you get.
Yeah.
Is it finite or you?
Yeah. So in fact, the primes that show up are bound. If you take somebody in S, the primes that show up from dense locally compact subgroups are contained inside of this set of primes. Yeah. Right. So and I think there's a lot of traction to get in. We actually go a lot further, and we recover many theorems that were known for S in the case of R, and we're able to get new theorems for S. But I think I'll end by telling you about some new examples we found. Because one of the things that we wanted to understand S, we wanted to get new properties, but on the other side of the coin, we had these weird P localizations. And what were those? What are they? What do they look like? So we get a few new groups in S. So the first one, and this isn't in, I should say that up until now, that stuff should be on archive within, well, as soon as I get done with my edit, so hopefully soon. This is some additional examples and things we worked out, which will come optimistically sometime this year. So we'll see. So if you look at the 2 localization of T5 plus, this thing is compactly generated, and it has a co-compact normal group from S. I'm curious to know if you can make this finite. I played around a little bit, but it seems a little difficult to do that. It's not clear to me how to make that virtually S instead of S by compact. If you look at D greater than 7, the alternating group, if you look at U alt D and you look at the 2 localization, this thing is compactly generated, and here we can prove S by finite. And you ask, well, why D greater than 7? Well, it's because the CeLO2 subgroup of alt is not self-normalizing in 2 alternating groups. It's alt 4 and alt 5. Yes, so that's where you get this 7 from. Yeah, so if you have D equals 6 and D equal to 5, this thing is not compactly generated.
Is 2 important here?
No, it's just let's see. You have to be a little careful about what normalizers look like. So the reason that we get compactly generated is because this thing is self-normalizing. The CeLO2 subgroup is self-normalizing in there, essentially. But if you have self-normalizing CeLO subgroups, you can get these. So yeah, I guess I would like to know more about what these things look like. I mean, they all act on trees. They act continuously, but not properly. And in fact, another thing that we discovered, which was very cool, is if you read Lebudek's paper about these almost prescribed things, which is a version of these kind of Berger-Moses groups, we're able to realize these things as this sort of almost prescribed business, but now you need to use illegal colorings. And if you're allowing yourself illegal colorings, you can write these down in a very concrete way in this sort of view of this GK of FF prime. And if people are interested, I can explain that at some point this week. But this was a lot of fun, and it really kind of gave us some new examples and gave us some new techniques to understand these canonical guys that are rather strange. And the one other thing I'll say, which sort of came out of, once we realized we were studying these groups, and we realized that we could look at illegal colorings to get a description of them, we went back and looked at Adrian's paper, and we're able to prove a proposition that kind of tells you exactly when these groups are virtually simple. So if you have this setup that Adrian uses, and of course if you don't, some of you may not have looked at the paper, but I thought there's probably enough people who would find this interesting. So if you have F containing F prime or transitive, and F is generated by its point stabilizers, then this group is virtually simple. And this doesn't require anything about, this could be a discrete group. It just tells us that they're all virtually simple. So if you read the article, there were some sufficient conditions, but we sort of nailed down exactly when this thing is virtually simple. And in the case that F doesn't act freely, then we get some more examples of groups in S. And so I will stop there. Thanks.
Question? Or comment?
Yes.
I have a group which many years ago I tried to think about it a lot, and I wonder whether it's in your class. Take the free profinite group.
Okay.
Take its abstract commensurability group, namely, all the isomorphism between
finite
finite
index.
index numbers,
Yeah.
and you identify two which are.
Right, right.
Is this in your class?
That's a really good question. Yeah, I mean, I guess. So I've thought a little bit about this, and I couldn't even come up with one element of this. You know, isomorphisms between finite index subgroups. Like, it seems sort of difficult even to come up with those.
No.
Well, they're different because they're free profinite groups, but they're different ranks, right?
No. If you take the same index, then they have the same.
Ah, right. Yeah, that's a really good question. So
The problem with this group is that the full automorphism group of the free group is embedded into it, as well as the full automorphism group of every finite index subgroup. So you're getting bigger and bigger
right.
kind of compact groups. So the normalized or finite index are big, and the question is what you get all together and whether this is a simple group.
Yeah, I like a lot that question, and in fact, I put it. So Mihail Urshov has asked me this has advertised this several times.
Let's start with the free property.
Yeah, and so I actually thought so I asked you this question about system normalizers, and the reason I did that was I had this scheme to show that if you look at the free pro P group or pro PQ group, you could do some kind of thing with system normalizers to try to rule out that showing up in the class R, but I didn't have much success. So this is a bit stronger, but you'd want, does the abstract commensurator live inside of R? But yeah, I like that question a lot. That's a nice question.
More questions?